what we talked about was our first definitions of acids and bases. We have the Arrhenius definition. It is super commonly used when looking at acids and bases. And in fact, if you have to move through more general chemistry, say 152, you'll look at the Arrhenius definition for acids and bases and then quantifying it and calculating it and all that fun stuff. Right? My opinion of it, for those of you that have actually downloaded the slides, have might guess that it's a little bit not the greatest. Because those definitions are super narrow. They really only look at water. Right? Which, taking a step back, why were we looking at water? Okay, so why did we use these definitions? Well, what is water? H2O. Okay, it's our universal solvent. We say, well, why is our definition for acid H plus and our definition for base hydroxide centered on water? Remember there was that other format we could look at water as? We look at it as HOH, which is really a way of saying we have H plus and OH minus. You mean an acid being one half of water and the other half of water being our base. So when in a water system, this definition works because we're ultimately breaking water down into its constituent parts, and we're naming the parts of water as acid and as hydroxide. For the instant we move into something that is not water-based, like pretty much everything we do in a synthetic environment, well, then these definitions fall apart. Okay? And that's where or at least my useless term comes into play. So we have a couple different definitions that kind of spread out of this. It starts with Bronsted Lowry, and that's really the only one that you're kind of expected to see. And what happened in the Bronsted Lowry sense is they went through and looked and saw there were some reactions that didn't fit this production of hydrogen ion and the production of hydroxide. Right? And so because of that, they wanted to alter their definition. Okay? So how did they alter it? In both cases, we're starting with an acid, reacting it with a base. In the first case, it makes sense. We have our Arrhenius definition of hydroxide is present. But do you see hydroxide in the second one? No. So what were Bronsted and Lowry looking at when they defined this new species as a base? And that becomes trickier. Okay? The first thing we can go through and do is try and decide what part of the molecule we need to be evaluating. Okay? Well, part number one might be that we ignore the sodium. Why would we ignore the sodium? Any ideas? Why should sodium be ignored? Salt-like, not neutralize. Not quite, because it's a metal. We can't quite get away with that. If it had been silver, I wouldn't be able to ignore it. If it was lithium, I'd be able to ignore it. If it was potassium, I'd be able to ignore it. Why would I ignore the alkali metals? If we go back to our solubility rules, rule number one says group 1 metals are always soluble, meaning they dissociate into their ions. The sodium ion doesn't react with anything. We don't care about it. What we care about is that second half. So what's a common feature for the base? What do you see as a similar pattern between the two species identified as bases up there? They have a negative charge. So we could go through and look at species that are negatively charged. Okay? But chloride, as a negative charge, isn't a really good base. So we do run into kind of exceptions there, but it's a starting point. Okay? And because the chloride didn't work for us, that's where Bronsted and Lowry had to shift the definition a little bit and ultimately said, well, what happened to that species? Okay, well, what does NH2 look most like in the product? NH3. What does OH minus look most like in the product? What did both of those species do in the course of going from reactant to product? They added hydrogen. In fact, they added H+. So what Bronsted and Lowry went through and did is said, well, I can't use the negative definition because I've come up with exceptions. So what I'll still do is run off of this definition of looking at the products. The acid I will still define as something that donates protons, or it has those H+. But the base I'll now define as something that accepts H+. And instead of added, we can say accepts. This broadens the definition enough that we can actually start to use it in a synthetic sense. And that's one of the reasons why the Bronsted-Lowry has kind of carried through a lot of kind of understanding and a lot of common definitions for acids and bases. Okay? It, again, unfortunately does not apply to all reactions. And that's why another Framus person came along and said, well, we need a new definition. We need a definition that's broad enough to incorporate all reactions. Okay? And what he was referencing then was what causes the bond to form. Okay? Well, what causes NH2 to be able to form a bond with that H+? Kind of last ultimate definition. What allows for the bond formation between H and NH2? What allows for any bond? So we can get with force. It's stronger than force. How do we have a bond? Okay, how would we show it? So we could say, show it with a line. We have this attractive force, but it's an attractive force that's ultimately applying to, Johnny? Sort of, are electrons. It's the exchange of electrons. It's the sharing of electrons that are causing this. So when I go through and look at my definition, instead of saying, I want to look at hydrogen ion or hydroxide or any of that, I want to say, I want to look at how the electrons are moving around, because the electrons are dictating if a bond is formed or not. Well, what is the base supplying? Well, it's negatively charged. Why is it negatively charged? Because it has extra electrons. Well, if it has extra electrons, what is the base supplying into this acid-base reaction? What is it donating? Donating electrons. What does the acid then supply into it? Well, the acid is H+. All it is the plus. So what is the acid doing? It's then accepting those electrons. Because we're now looking at the arrangement of electrons, okay, Johnny already started to allude to when he said it very quietly, and I doubt most of the class heard, okay, on the origin of this definition. We're looking at the ability for atoms to share electrons with each other. We saw this before when we looked at the sharing of atoms or sharing of electrons between atoms to draw what? Lewis dot formulas. Guess what this definition is referred to? It's the Lewis definition of acids and bases. We expand the definition far enough out that now Lewis definitions of acids and bases apply to virtually every reaction out there. It's the ability to share electrons or accept electrons from another species. Okay? That definition is now so broad that it rarely gets used. Okay? It's like defining humans. Okay? It has 2 eyes and a mouth. Okay? Yeah, humans have 2 eyes and a mouth, but there's a few other things that make them human that might help if we refined that definition down to a little smaller sense. Even though it may not apply as universally, it covers most everything. Okay, so the Lewis definition applies to everything. Bronsted Lowry applies to kind of the next most and tends to be the most well accepted and used. When you're going through and doing calculations, if you have to move into a 152 class, that kind of sucks to deal with those calculations, but almost all of those calculations are based off the Arrhenius definition. Okay? So they're just different ways of looking at and defining our acids and bases. That's all we really need to get out of it. Okay? We already started to allude to this idea of conjugate acids and bases. So let's start with that top equation. Okay, I've got two species. I want to react those two species. How should I react them? Well, one needs to be an acid and one needs to be a base. I need to be able to look at that formula and identify which one's which. Okay? So what was our acid definition? It can be positive, but that wasn't a definition of it. We could go through accepting electrons, so that could kind of work back to James' idea of positive, the accepting of electrons. That definition, again, was really, really kind of out there. That applied to everything. And we want to narrow that down. We want to narrow that down into something that's more useful. So we've come across at least 3 solid definitions on acids and bases. One, when we went through and looked at nomenclature. When you look at a formula, how do you know it's an acid? AQ and hydrogen. Where did the hydrogen have to be? In front. Okay? So that works as identifying an acid. Okay? Other options, well, we need to just find a hydrogen. And it's starting to piece together other kind of clues to help us work our way through to decide that. So when we look at those two compounds, which of those could be our acid? Why H3O? I would step away from the charge because we don't need to go that far. It has hydrogen, period. The other one does not have hydrogen, so it can't act as an acid. So if I'm looking at an acid-base reaction, only one of those can possibly be an acid. If it's going to act as an acid, it needs to then produce a product. Okay? What would that product be? So if H3O plus acts as an acid, what is it doing? It is losing a hydrogen. So the formula should become H2O. What should happen to the charge? It should become neutral. We're losing H plus. Well, if it started positive and it loses a hydrogen and it loses a positive hydrogen, what must the charge then become? Neutral. We've lost that positive. So that would then become the product of looking at H3O plus acting as an acid. Where did that hydrogen go? It would have to go to our base. Well, so let's evaluate what's happening with our base. SO3 minus 2 is now by definition going to have to be acting as our base. What happens to our base? What does the base need to do? So we could go through the donate electrons. Again, that's our Lewis definition. We don't want to go that far. We want to sit in the Bronsted Lowry hole. It accepts a hydrogen. So what happens to the formula? It should become HSO3. I've added the hydrogen to my formula. I still have SO3. What should the charge become? Why should it be -1? It's accepting H positive. It started already as a -2. We accept a positive, and we were originally at a -2. We're going to reduce that negative down to a -1, or change the negative. Make sense? Yes?
So would that create another acid? Since the hydrogen's...
That's an interesting question, and one that I'm going to hold on to, because you might take a look at the next one, which will actually turn into a quiz, just to be irritating. But we aren't there yet. You know me. I'm always irritating. I have to make up for last week. Share the pain of my headache. What happened to H3O plus? H3O plus became H2O. Okay. What else is kind of different or interesting about actually both of the reactions shown here? It's different than anything you've seen so far. We've seen H2O before, we've seen HSO3 before.
What is split between both the hydrogen?
So what you might be saying is typically when we want our reaction, we would try and neutralize that, and that should be H2SO3. Is that what you're saying?
Yeah, or like usually we just do like double replacement, zero replacement.
When we've done our reactions before, we usually do a full swap. We do a full exchange. Okay? Notice in this case, we're not doing that. In our acid-base reactions, we do one transfer of hydrogen. Okay? If we want to do more, we can, but that then gets added on as a second reaction, okay, or a second equivalent. At this point, we're just running it as a single transfer. Okay? There's another big difference. What's that? There's a double arrow. We see the arrow going to the right. We've seen that before. But what else do we have? An arrow going to the left. What does that mean? The reaction can go both directions. The reaction is reversible, okay, which is going to get us into the concept of equilibrium, which is a challenging concept. So we'll look at that in a little bit detail. Okay, but the reversible part is the part that we want to kind of evaluate. H2O, to reverse this reaction, must act as what? H2O, to go back to H3O plus, has to do what? It has to gain a hydrogen, which means H2O is acting as a base. Okay, by that same token, let's take a look at the HSO3 minus. What does the HSO3 minus have to do to run the reverse reaction? It has to act as an acid. It has to get rid of that hydrogen. Anybody see a problem potentially arising here? Since I don't hear any rapid answers, let me then ask a question for you. What species is the acid? Okay. We have a bit of a problem. If I ask for the acid, well, in that equation, how many things are labeled acids? All of them are labeled acids? SO3 minus 2, is it labeled an acid? No. Is H3O plus labeled an acid? Yes. Is H2O labeled an acid? Okay. It has an H. In a future reaction, could it act as an acid? Sure. In this reaction sequence shown, is it acting as an acid? No. Okay. It's one of the reasons why I labeled it. HSO3 minus? Acid. So if I ask for the acid, we run into a bit of a problem because there's two acids, and they aren't the same thing. So how can we clarify our statement to make sure that when I ask the question, what is the acid, you can be like, oh, it's this answer and this answer only. Okay. There's a little bit of a hint on the slide talking about this idea of conjugates. Okay. Believe it or not, and this kind of comes down to some debate apparently according to the final, which is something I grade for accordingly. When I ask for the acid, that's the species I'm asking for. How do I make sure that you don't say HSO3 minus? Or let's say it a different way. I want you to say HSO3 minus as the correct answer.
Is that the product? Is it actually the product?
It's a product, so I could say, what's the product acid? That's a little bit weird. It's a product. It's not really acting as anything. Okay? This is the issue of conjugates. If I want you to say HSO3 minus, I'm not going to ask for the acid. I'm going to ask for the conjugate acid. Our conjugates are the things on the right-hand side of the equation. Incidentally, what does conjugate mean? Anybody have any questions about conjugate? You're like, oh, that makes sense. Totally understand it. Should I make that the quiz? Define conjugate for me? No? Okay, so accept that you don't know. That's okay. Have you heard of conjugal visits? No? Okay. Conjugal visits? What?
Like periodical, right? Say once in a while, like.
Okay, it's usually a relation. Conjugal visits are like in prison, you can have a conjugal visit. You get a particular person can come in and visit with you and potentially private situations. Okay, you're usually looking at people that have strong relationships. Okay, usually partners, like husbands and wives. What's happening when we're referencing the conjugate? It's the thing most similar to it. So what is the conjugate partner of H3O+. It's effectively the lover. It's the thing that looks most like it, most similar to it. It's H2O. The conjugate partner of H3O+ is H2O. Because H3O+ is acting as an acid, what must the conjugate partner act as? The base. It must act as its opposite. So if I want to know the conjugate acid, it's HSO3-. Okay? That's how I would differentiate it. We do have a slight issue with that nomenclature or moniker system with that double-headed arrow in there. Because that double-headed arrow says that we can run the reverse reaction, which then means the products become the reactants and our reactants become products, and now our labeling system becomes a bit odd. So our acids and bases are typically referenced only on the left-hand side of the equation, and our conjugates are on the right-hand side of the equation. Okay? It is a way to clarify the system. That's it. Okay? That's the point of the word conjugate. It's allowing us to see that. Identifying the relationship is just looking at it and saying which structure looks the most. They're conjugate partners. Kind of makes sense? Okay? So with that, I'll have you go through as a little quiz. Actually, I think that's a pretty big lie because I don't think I have any sheets. Oh, never mind. Look at that. I thought ahead. Sorry, I didn't mean to get you too excited.
Looks like you don't have enough there.
There's quite a fight. So let's take a look at the answer. What answer do I want to do? Actually, let's pause that. Write down, right? Let's see it. So the answer that everybody came up with should have been so if we had to go through and label, this acted as a base, this acted as an acid. Right? Everybody get that?
No.
What did you get?
Reverse reaction. Just reverse on which one.
Oh, so it was already written, but just reversed. Well, what's wrong with what I did? To act as a base, what does it have to do? To lose a hydrogen, gain a hydrogen. If it acts as a base, it gains a hydrogen. Yeah, it gained a hydrogen. The other species, to act as an acid, would have had to donate a hydrogen. What's wrong with it?
So there's multiple right answers?
Ah, yes. There are multiple right answers. How do we decide which is correct? Which one's the acid and which one's the base? Well, the definition system that we've got to work with so far is that our acid has to have hydrogen. Which one of those has hydrogen? Well, both have hydrogen. So how do we decide which one's the acid? That's a good question.
Go back to the first definition we had, and since H2O has OH in it.
We could try and go back to our first definition and looks at OH minus. Okay. OH would suggest then that that would act as a base. It's being acting as an acid here, so I'm not quite sure where that's going. How do we decide which answer is correct? We don't have the tools to decide. You're not given the tools to decide at this point. What you're given are the tools to be able to identify acids and bases based off of a reaction shown. That's where you need to function. Okay? What I'm trying to show you here is that there are limitations to that definition. That definition does not work perfectly. We have to come up with other rule sets to be able to decide which is acting primarily as the acid or as the base. And we'd have to evaluate those rule sets to decide which is a better reaction to run. Okay? Is it something that you are able to do at this level? No. Okay? But that is where chemistry becomes interesting. You look at two possible valid answers according to definitions and decide which of them is more correct because you understand something about how atoms work. Okay? That is chemistry, not the rest of the mumbo-jumbo conversion nonsense that we've been doing most of the semester. You can see where my loyalties lie. Okay? So if you're interested in trying to determine how you would know which answer was more correct, okay, HSO3 acting as a base or as an acid, that really relies on organic chemistry, okay, and predicting something about each of those individual reactions. That, believe it or not, isn't that difficult, okay, but it gets sold as this big difficult package. Okay? Why do this? Because I think you should take OChem. Okay? Just my 2 cents. Okay? Questions about what's up there? You understand how you identified acids? You understand how you identified bases? Yes. You understand what the conjugate partners are? Yes. Then what you've got is exactly what you need out of the acids and bases. Okay? And we've got a whole bunch of slow stuff. We can go through and look at all that. Whoops. Okay, but let's get to kind of the key point here. What's going on with that double arrow? Okay, as what was already addressed, that is your reversible reaction, which is equilibrium. Okay? One of the things that we could go through to decide how our individual species acts, notice the reaction I'm showing here is the one that probably most of the class showed, right? Okay. On how it went through and reacted. Okay. Deciding that that was a better reaction than the one I showed could be done through kind of simple looking at stability of atoms and where electrons would like to be, OChem. It could also be gone through and looked at by defining hardcore quantification of how many moles of one species are present in comparison to the moles of the other species through careful calculations, also known as CHM130. Okay? There's an entire semester devoted to equilibrium, and yet it's one of the things that we're supposed to cover this semester. Okay? But you're not required to do any of the real calculations behind it. Ultimately, what equilibrium is looking at is the balance of products and reactants. When I run a reaction, all reactions have the potential to reverse. How much do they reverse? In 130, they tend to reverse very small amounts. And 151, they reverse very small amounts. Those amounts are so small that we generally just say the reaction goes from left to right and we're done. Okay, we ignore the reverse reaction. But there's lots of different systems where the reverse reaction becomes very, very important. Like, I don't know, how we breathe. Okay? That process of transferring oxygen from the lungs and CO2 from the muscles to those respective places is a reversible reaction. If it was not a reversible reaction, we'd have a hard time breathing. Okay? So we need to take advantage of that chemistry. We need to understand something about it. The big thing that comes out of it is this famous, I think, French guy, Le Chatelier. The Le Chatelier principle. Once our reaction gets to an equilibrium state, okay, and we'll define what an equilibrium state is in a second, it will do whatever it has to stay at that equilibrium. Okay? So once you've achieved balance and someone comes by to push you, what do you then do? You could fall. Most people probably catch themselves and rebalance. Okay? Unless you had some inner ear issue like me, in which case you'd probably just fall over. Okay? But then you'd get back up and you'd achieve rebalance. Okay? So our reactions are always trying to achieve that balance. So we're doing whatever it has to do to achieve that balance. Okay? But if we get pushed, it's not like we all of a sudden make new parts to then shift our balance. What do? We shift our weight and kind of adjust backwards. So we change where our weight is located. But we don't make new weight, we just change how it's located. What we're looking at with our reactants and products is effectively the same thing. Our reactions will scale to make sure that they've achieved that balance. So if I have too much reactants, it'll shift to make more products to achieve that balance. So what do we mean by that? There's two kind of comparisons that we could use. Okay? Though allegedly, from what I understand, seesaws are starting to disappear and making a mild reappearance on the playground, so maybe nobody's aware of a seesaw. You guys aware of seesaws? You got a plank, and you got a fulcrum in the middle. Right? And ideally, when we draw that fulcrum in, it's right in the middle. Whoops. Right in the middle, so we can have our two little happy kids with hunchbacks. Sitting our seesaw and with weird arms. And they can jump up and down and they balance. Oh, hey, this is fun. Okay, we'll do the same thing with our equilibrium though. So let's get rid of my weird kids. Okay. And we have reactants and products. The reactant we'll call our blue box, and our product we'll call our red box. Okay. Would I be at equilibrium now? Ballpark. Okay. Those boxes are roughly the same size. So what happens when they're on there? It would balance out where that seesaw is perfectly levitating. Okay? The reaction is now at equilibrium. Okay? As a chemist, we're trying to make something. So our reaction has achieved this equilibrium, and I want to make something. Well, the something I'm making is the product. Okay? So what do I want to do to the reaction? I want to remove the product. So I remove some of the product. Am I now at equilibrium? No. It's going to shift. Okay? And we'll see an imbalance to it. Well, now the reaction says, well, I need to re-achieve balance. How does it re-achieve that balance? Okay. And we always hear this shift the equilibrium. Okay. The equilibrium is effectively the triangle in the middle. I can't change that. Every reaction has a pinned point. So when we're saying shift the equilibrium, what are we saying? Go ahead.
Balancing the actual equation?
Not even that. You're getting to chemistry. We just have these two boxes. How do I make sure that I get back where it's a level plane? Less, and I could add more boxes, but I said I can't add more. Okay, that's fixed. That's now done with the amount of total things. Okay, so what I could do is get rid of some of the reactant. Okay, but we said it's fixed. So if I get rid of some reactant, I can't just destroy it. Okay? Because the reaction is now all by itself. The reaction is doing this. It can't just destroy that matter. So what could it do? What could it do to get rid of that reactant?
Put it in the middle.
There is no middle in a reaction. We have a reactant and we have a product. Where did the product come from? The reactant. If I get rid of the reactant, where did I get rid of the reactant to? Product. What ends up happening? I get a little bit more product and a little bit less reactant. What's now the result? I can re-achieve that balance. Being a chemist, what do I want to do? Remove product so I can remove more product. As I remove more product, the reaction is now further out of balance. What happens? It takes some more of that reactant and it turns it into product. So if I constantly remove the product, eventually what happens?
Generate.
It'll be unable to regenerate because I'll run out of reactant. I will have converted all of my reactant across to a product by slowly pulling the product out. So a reaction that, say, doesn't produce a lot of product right away, if I'm careful about how I can selectively remove product, I can eventually get it to all convert across to that product. Okay? So one of the questions that usually comes out of this is then, will then all reactions have equal amounts of reactant and product? Is that true? No. Some reactions produce a lot of product right away. Well, but then this doesn't work. What changes about the diagram if I say have a system that has its equilibrium where I have tons of product and a very small amount of reactant? It's going to be unbalanced. It can't be permanently unbalanced, so something has to change about this where this is now balanced. That is the equilibrium. What are you saying, Johnny?
I was going to say maybe the volume change, like now
believe it or not, we could deal with that. You're getting too physical on it.
Yeah.
Pull it really simple back to this.
Okay, because maybe like when it was the bigger box and it was like half, maybe the blue box is more than.
Nope. I don't know what you're trying to do. You're trying to play mind games and say, well, really, Mike's saying that the blue box is the equal weight of the red, or the same weight to be at equilibrium. No, the red box has tons of mass, tons of product, very little reactant. What has to change about this diagram to make sure that we're still at equilibrium and that plank is flat? We can't take away product.
What has to go back to?
Nope. We're at equilibrium. It is flat. This thing something about this picture must change to ensure that I have a flat line where there's a giant box on the right and a tiny box on the left. What do you think, Sky?
Break down the product.
Nope. That's what she was suggesting too. Product is formed. Done. Tons of product.
Reverse the reaction?
Nope. You're trying to, again, reverse it. This is the reaction. We have that tiny amount of reactants, that tiny amount of products. The bar is level. How can all of that be true? What has to change about this diagram for that image to be true? Say that again? The equilibrium was our triangle, the fulcrum that caused the balance. Okay? Every reaction has a different equilibrium, a different fulcrum to cause this balance. So when we're looking at a reaction, I can have reactions where tons of product are formed. Okay? For me to still have that equilibrium, what has to be true? That means my fulcrum must have shifted. Does that make sense? I can define the location of that fulcrum by looking at the relationship of the products to the reactants. Okay? That fulcrum is located more on the product side than on the reactant side. So if I look at where my fulcrum is located, okay, closer to products than reactants. Mathematically, I could say products over reactants. Okay? If I have a lot of products and very little reactants, the number that I get will be closer in value to the products than it will be to the reactants. Okay? If we flip it, what happens if I slide the fulcrum all the way over to the reactant side? What's going to change with my image now? It'd be unbalanced. So now I want to say my fulcrum's over here. Okay, to have the fulcrum over there, what has to be true? I need more reactants than I have products. Okay? So when we're using this analogy for our equilibrium, it doesn't mean we have equal amounts of reactant and products. I can have unequal amounts. The amount or the relationship between those amounts is ultimately decided by where that fulcrum lies. For every reaction, it is defined. Okay? Or it can be defined. It is something that is defined. Whether we have defined it or not, discovered it, is the next question. Some reactions have that fulcrum dead in the middle, which then means I have equal amounts of reactants and products. Right? Most reactions are not dead in the middle. I have some imbalance where I'm favoring products or favoring reactants. As a chemist, where do I want that fulcrum to be? In the center, I have equal amounts of reactants and products. So when you go through to make a sandwich, you have to make 2 sandwiches, or attempt to make 2 sandwiches, right? So you can make one, but then you have all the parts left over for the other one, and you couldn't make it out of those parts because you were horrible at making sandwiches. Okay? Is that an ideal situation? What's your ideal situation? You only have products. Our ideal situation is that our fulcrum is located where? In the center, I have equal amounts of reactant and product. So to make one sandwich, I need the fixings for 2 sandwiches. Right? Because I have to have leftover reactants to balance it out. Where's the ideal situation? On the far right. Because then how much reactants do I have left over? A very tiny amount. Ideally, all of my chemical reactions produce tons of products. So that when I go through and look at the relationships of reactants to products, I get a very large product value and a very small reactant value. So when I define my equilibrium, I get a large value. That's a good thing for chemistry. Small values tend to be not good things because we get a lot of reactants. Okay? If you went into the lab and you ran a reaction and all you saw were reactants, that'd be a very exciting lab day. Okay? That would kind of suck. The whole point is going into lab, you mix some stuff and stuff happens. Okay? We're hoping to see product. Kind of make sense? Okay, the other analogy that can kind of come out that I've heard that I kind of liked was two divided chambers, okay, with an opening down at the bottom of that. Okay, that opening I can open and close at will. So I'm going to keep it closed for the moment. The left side will be my reactants. The right side will be the products. So I've got this reaction in here. So when I start a reaction, how many products do I have? 0. So I'll just fill my reactant chamber. Okay? But I'll tell the reactants, you can't react yet, can't make products, just chill as reactants. And then I say, okay, reaction, go! And I release the bottom layer. Well, if we assume our reactants are like a liquid, what happens to the liquid? That liquid drops, and then it starts to rise up the other side. How far does it rise up the other side? Till it's what?
Equilibrium.
Till it's equal. You mean till it's reached equilibrium? Yes, exactly right. Does that mean there's no liquid flowing between the reactant and the product side? No. I still have molecules on the reactant side going to the product side. I still have stuff on the product side moving to the reactant side. What has happened when I've reached equilibrium? It's not that motion has stopped or the reaction has stopped. What's happened? The rate at which reactants become products and the rate at which products become reactants becomes equal. You mean again, equilibrium? Yes, I do. That's what it's referencing. Okay? So what happens now that we're at equilibrium? Le Chatelier comes in with this example and says, let's mess with the reaction. So let's put the barrier up, say, okay, reaction can't do anything right now. Okay? And I'm going to add more reactants. What happens when I say now reaction go? It won't be equal, so what happens? Stuff from the reactants flows to the product side goes up, the reactant side goes down until a new equilibrium has been achieved. Okay. What else could I do? Pause the reaction. Don't react anymore. What else could I do instead of adding reactants? I could take products out. So I remove some products. And now I say reaction go. What happens? It has to re-achieve that equilibrium by doing what? Converting the reactants. The reactant amount goes down and the product amount goes up until we re-achieve a new equilibrium. What else could I do?
Didn't we cover it?
Nope, we've got more. I could take out reactants. So I pause the reaction. I can take out reactants. What happens when I remove that barrier? Products move back to the reactants, and I re-achieve a new equilibrium where I've lost products and gained reactants. Make sense? We could again say, oh, but that means, Mike, doesn't everything equal 1-to-1? Everything has to be equal amounts on both sides. Well, not necessarily, because we could change the size of the chamber. If I change the size of the chamber, do I have equal amounts on both sides? No. Okay? So we have to remember through these analogies that it helps us see that balance, but we're not saying there's equal amounts on both sides. We're looking at the relationship between how much reactants and products we've got. Kind of make sense? Okay. Right, so, well, why were you talking about this in the context of acids and bases? Okay. Almost, not yet. What's going to affect the rate? Okay, so when we said we talked about this, we had our reaction that balanced out. When we're at equilibrium, the rate forward must equal the rate reverse. What's going to affect the rate? What's going to cause those particles to move faster across the membrane? Okay, we could look at how much the doors open. Let's look more at the substance itself. Let's say I put in a bunch of ice. Why are you laughing? No, it's a serious question, because I think you're laughing probably for a good reason. I could be wrong, but why are you laughing about drawing the solids in? Or are you just literally laughing at my drawing? That's what you're laughing at? You're laughing at the drawing? Oh my gosh. Why would ice cubes be a silly example? How much are the ices going to shift across? They aren't. Why not? There's no liquid on the left-hand side. Getting at the concept, if I put solid in, what's going to happen to the rate of the forward? It's not going to move across. How can I make it move across faster?
Liquid.
Make it a liquid. How do I make it a liquid? Add heat. Add heat to your reaction. What happens? Your particles move more. The more they move, the more likely they can transition to becoming a product. Okay? What else could we do to get our particles to interact with each other? How many of you are interacting with the people outside the room right now? That might be a bad, hopefully not a bad question. How many people are interacting with anybody outside the room right now? Okay, one out of most of the class. Why is only one interacting with people outside of the room as opposed to the whole class?
It's easy.
Doors are closed.
What's that? Go ahead, yeah. The doors are closed. There's a physical barrier preventing you from reacting with the rest of the world. When you look at your classrooms, they're behind closed doors and walls. Why do we not have our classrooms outside in the lobby?
We get distracted.
We'd get distracted by seeing everybody else walking around and talking about their own conversations. You'd see different teachers yelling and screaming and nothing would work. You'd be like, oh, what's going on over there? Right? We're trying to close you off so that you can only focus on what's happening within here. So when we're looking at a chemical reaction, what do we need to do? We need to make sure that there aren't physical barriers. We need to make sure that everything's in the same phase, also known as, Elizabeth, it's good timing because you're looking down at your phone. Everything's in the same phase. What do we need to be looking for? Everything's in the same phase as opposed to multiple phases. Thank you, Jake, for jumping in and saving. We would need a homogeneous system. We need homogeneous phases or homogeneous reactions. So when we talked about homogeneous and heterogeneous, why do we need to know those? Well, how do we change the rate for a reaction? We need to have everything in the same phase so they can interact. How do we know we have the same phase? Well, we have to know something about solubility. We have to know something about our double replacement reactions, solubility rules. All of those things stack and pile into this. Okay? And they're relatively simple concepts that you could probably come up with. You just don't realize they're happening around you. So when we're looking at concentration, I need two particles to interact with each other. Okay? You're trying to find a spouse, okay? Or a significant other. Maybe let's not go all the way to a spouse. A significant other. Okay? What are the odds you'll find a significant other if you never interact with anybody ever? 0. Okay? Because the concentration of the significant others is 0. And to have a significant other, well, you have to encounter them. So what happens if you encounter one potential significant other? Well, there's some likelihood that you found a mate, but probably not. Okay, what do you need to do? Increase the numbers. Have a whole bunch of them. Okay? A whole bunch of possible interactions. We need to change the concentration. You mean like molarity? Yes. Like molarity. That's why we use molarity as a unit, because we need it to determine what's going on with rates. Okay? The nature of the reactant, what we're talking about there, the phase. Okay? If I'm trying to interact with someone, I want to make sure that there's not a phase barrier between us, that we're all in the same phase system. That's our homogeneous versus heterogeneous. In a heterogeneous system, where do the two phases interact? Only at the face where they touch each other. Okay? That's a relatively small surface area. Okay? That's looking at the nature of the reactant. I want to make sure they're all in the same phase so that they can react with each other. Okay, mechanism. How does the reaction proceed? Okay? For the reaction, to find a significant other, do you have to stand on your head every single time? Okay? Do you have to do a little dance? I don't know. Okay? But that's going to change the odds of how you find a significant other. So we're looking at those relationships and what things affect those. Okay? The big thing that comes out of this is collision theory. Okay? If you had your pen and just told you to blindly cap your pen, okay, and actually maybe put on some ski gloves so you can't feel which ends you're holding on to, and you're just trying to blindly cap those, what are the odds you're going to be able to do that really well on the first try? Not very good. But what if you change the sensitivity of your hands so that you can feel a little bit better on what you're working with? That will change how the reaction proceeds, and that will change the success of the reaction. Okay? Realize that when we're looking at chemistry, what is happening sort of is this invisible force that has ski gloves for hands jamming stuff together, and magically it all of a sudden works. Oh, that worked. Great. Something moves forward. Okay? That's effectively what's happening on the chemistry level when we're talking about chemists sitting in the lab. Okay? Imagine somebody in a giant suit, space suit? I don't know, big suit with hands that can't touch things nicely. Let's just skip that. Let's just move on. Temperature, catalyst. Okay? A catalyst, something that comes in to help the reaction out. So you're trying to cap that pen, but your friend comes up and says, here, let me help you with orienting those things. Now you're properly oriented. Now you can put it together. They've helped you do the reaction, but they aren't consumed in the reaction. Okay? So looking at those individual pieces and how they affect the rate is a large part of what chemistry does. So when we talk about the units that we're looking at and different measurements, it's all coming back to looking at our reactions and quantifying them and defining them. Okay? Is it a challenge? Yes, but that's also what makes it cool and interesting, is we're trying to come up with ways to quantify the observations that we see. Okay? So why talk about it when we're looking at our acids? Okay, so we've got two compounds I want you to think about, H2O and HCl. What do they have in common? Hydrogen. So both of those compounds you could define as an acid. Oh crap, well if H2O is an acid, I'm never taking a shower again, because it should have melted my whole face off by now. Why are we not concerned about water as an acid? It's a weak acid. How is it a weak acid? Doesn't water produce H plus just the same way that HCl produces H plus?
I would say it's not about the charge, but more what it's mixed with.
You can mix anything with HCl or water. That's not going to change necessarily the reactivity of the HCl in the water. Whatever else you're adding it to may change the reactivity because the other thing is reacting. Okay? But water and HCl are both producing H+. Why am I not concerned about water, but I am concerned about HCl? Go ahead, Johnny.
Water's got the negative H.
The negative OH. HCl has the negative chloride, the negative Cl. So I don't quite accept that. The dangerous thing is that H+. Oh God, that's horrible, H+. Okay, so we've got two diagrams set up here with our fulcrums, trying to evaluate it. H2O. Anybody know where H2O's equilibrium is established for H2O to H+? If H2O's fulcrum is way on the left, what do I have to change about my image?
Decrease.
Decrease what? I need to decrease the red. What did the red represent? The product. Which product? Which product? H plus. How much H plus is produced when I look at water? Tiny, tiny amount. Why is HCl so dangerous? What does HCl's equilibrium look like? There's HCl. It is shifted way to the product side, meaning when I add HCl or look at HCl, it produces H plus in insanely high amounts. Okay? The H plus is the same in both cases. It's the amount that's dangerous. Okay? The amount generated from HCl is pretty much a 1-for-1 relationship. The amount generated from water, 10 to the minus 7. Okay? Tiny, tiny, tiny concentrations. Okay? It's the concentration that'll kill you. Which kind of sounded like a joke. Okay? So, our equilibrium is our balance of products to our reactants. It's how those different things are established. That is then defined as this capital K thing. Okay? Lots of calculations come out of equilibrium. That is the entire second semester of Gen Chem 152. Okay? So, strong versus weak. Okay? So what we could go through and do is, well, we could spend the rest of the semester doing everything that's covered in 152 in a semester in one lecture. That's a bit of a jump, particularly if you talk to any 152 students. Okay, so we want to come up with some other way to recognize our strong versus our weak. So our strong acids completely ionize, like HCl. When I add HCl to water, it instantly becomes H plus and Cl minus. I get tons of H plus for every Cl ion. Okay? When I add water to water, it doesn't really ionize. I need 10 to the 7th molecules, or an insanely large number of molecules, to even produce a tiny concentration of H plus. So I have a weak acid or base. So what we're saying with our weak acids and bases is that they ionize to varying extents. Okay, well, one of the things we want you to get out of acids and bases is being able to recognize the difference between strong acids and bases. Well, we said we're going to look at these stupid little fulcrum seesaw things. Okay? That's a bit annoying to have to look at for every single reaction. There must be a better way to identify our strong acids. There is. Guess what it is? Begins with M. Not quite. At all. At all, really. Sorry. You have to memorize. Our strong acids are defined as perchloric acid, sulfuric acid, hydroiodic acid, hydrobromic acid, hydrochloric acid, and nitric acid. Okay? Those are our strong acids. Are there other acids that are stronger? Yes. Why do we only memorize these as our strong acids? Well, do you want to memorize more? No. There's your answer. Okay? Our strong bases. Okay? Lithium hydroxide, calcium hydroxide. Group 1 and 2A cations bound to hydroxide are our strong bases. Why hydroxide? What was the Arrhenius definition of a base? The production of hydroxide. Okay? So how do I know I have a weak acid or base? It's not on the list. That's how you know. Okay? For those of you panicking and saying, oh, I got one more thing to memorize, don't panic too much yet. This is officially what you would be supposed to be doing. You're not really expected to have these memorized at this point. You're expected to be able to process your acids and bases. So don't freak out too much. If you have to move into, say, 151 and 152, having those memorized becomes important and valuable. For 130, it's not that valuable. Okay? Probably valuable at all. Okay? The last kind of bit that we would go through is thinking about safety. Okay? We said that it's the concentration that'll kill you. So I could shout out, hey, Timmy, watch out for that 0.15 molar H plus solution because it'll burn you. Okay? Or I could say, hey, Timmy, there's a solution that is 0.15 molar of a strong acid, then you should be really careful with it because it'll burn you. How many of you knew about molar before the semester started? Do we teach molar to our little kids? No. How many of you were like decimals? Yay! How many of you were like exponential factors? Yay! Okay, so we didn't teach you any of that. Okay, what did we teach you about acids and bases, particularly when it comes to safety? Okay, what did you use to quantify it as a strong acid? The what? The pH scale. The pH scale is a way that we took our concentrations of our acid and we converted it into a number that didn't involve decimals, didn't involve exponential factors, and allowed us to very quickly just tell someone, hey, that's a pH 0 solution. Watch out. Okay? That's a lot easier to tell Timmy to watch out for. Anything smaller than 7, avoid. Anything higher than 7, avoid. 7, good. Okay? That's relatively easy to teach. That's what's happening when we look at our pH scale. It's about safety. How do we determine our pH? Okay? That's our highs and lows. Okay? The useful scale that you're used to seeing, 0 is strongly acidic, 14 is strongly basic. Why do we pick 0 and 14? Well, it's ultimately coming from the primary solvent used when we're looking at acids and bases, which would be water. The 0 and 14 are not really an artifact, but a characteristic of the concentrations of hydrogen ion and hydroxide ion produced in water. That's where the 0 and the 14 are coming from. How do we determine the pH? Okay. It's the negative log of the hydrogen ion concentration. So the hydrogen ion concentration for really dangerous solutions is usually an exponential factor, 10 to the power of something. That's dangerous. That becomes down to the 0 scale. We can quantify that relatively quickly. Why do we only show the 0 scale or the 0 to 14 and then not tell anybody about the negative log? What's the issue with negative things? When you have negative money, you're like, whoopee! No, that kind of sucked. Okay, when you're in a negative mood, you're like, whoopee! No. Negative things are bad. They inherently make life difficult. So we now have a scale that exists because we're using a negative. Okay? So we tend to not tell people about the negative. The next part would be the log. How many of you know anything about logs? Talk to me after class because I would like to know something about logs. Because I literally know very little about logs. Okay? I know how to use them, and that's about it. Okay? And yet, we're now using a negative and something that, admittedly, I should know how to use because I sort of teach them. Okay? But I really don't have an excuse. I really should know them. Okay? But you're looking at the person that uses them and teaches working with them and who doesn't understand what they are. Okay? To make pH. That's an arguably weird or odd system to use, but that's the system we use because it gets us to numbers that we can almost count on just our hands. Okay? Maybe if we were mutants. Okay? I think the last kind of thing here that I really think I can cover in a minute, okay, would be this concept of electrolytes, which you probably already know about because you did the lab last week. Electrolytes are anything that when added to water completely ionizes. Electro for electrons. And electrons are typically found in electricity. Okay? So when we're talking about an electrolyte, what's happening? We have a solution that has electrons that cause a light to come on. That's literally what's happening. We put current through the solution and a light comes on. We now have an electrolyte. Okay? So ion concentration allows for the passage of electric current. That's an electrolyte. Strong acids, strong bases, completely ionized. By definition, strong electrolytes. Sodium chloride. Rule number 1, according to solubility, always soluble, strong electrolyte. Calcium carbonate. Because we all memorized all of our solubility rules. not soluble in water, which then means not going to be an electrolyte. Iron hydroxide, not soluble in water, not an electrolyte. Silver bromide, not soluble, not an electrolyte. What happens when we move down to these bottom compounds? What's the issue with those? What do you mean memorize them? What is different about the bottom line versus the middle line?
More than 2
There's no metal. The middle line are ionically bonded compounds. The bottom line are covalently bonded compounds. Covalently bonded compounds are covalently linked, meaning they have strong bonds, which means what happens when we add them to water? They, by definition, can't ionize. Well, if they can't ionize, you don't have ions. If you don't have ions, you don't have electrons. If you don't have electrons, you don't have a current. The bottom ones are non-covalent compounds, tend to be non-electrolytes. Okay? And with that, I know I talked 2 minutes extra, but that was the last slide.